to infinity, what makes numbers interesting? So from the very childhood, we have been learning numbers, and still we are still in the process of learning about numbers. So it is a very interesting subject, and it's a very vast subject. So to talk about numbers in 1.5 hours is absolutely nonsense. So it takes a lot of people are still doing a lot of PhD on number theory. But today I am not going to talk about number theory. What I'll try to do is try to somehow familiarize with, recollect of those numbers we know, and also try to input some of the new numbers, some of which you may never have heard so far. So let's start the seminar. So I'll start with Nepal. So you can see this is a presentation I made in Korea, Busan, Asian Mathematics Conference, July 2, 2013, so 8 years back. So I made this presentation on Lisabi numbers system of Nepal. So I'll show some of the slides which I presented over here. What this is, you can see, I'm presenting this my slides over there. So let's recollect that Lisabi period is document history of Nepal is traced back to the Lisabi period that dates to 3000 AD. So very really historical is before it's 300 AD. In the history of Nepal, the Lisabi period is taken as 300 AD to 800 AD. The stone sculptures and metal statues of the period proclaim this period as the golden period of Nepalese art. A lot of temples has been built, and a lot of these manuscripts were there. So the first king of Lisabi period was Jayadeva I. The fourth Lisabi king, Manadeva I, was of historical importance because he built Sangu Narayan temple with the stone sculpture. The first, and there we see the first numbers there. So the first inscribed number is there. This is the Sangu Narayan Mandir. And I think you must have visited Sangu Narayan several times maybe. So look at this statue over here, this pillar over here, the historical one. So if you look at this pillar, so down below we have the number written here in this way. I'll blow it up. So the numbers are there. So this number, which we can't convert to, so this is Lisabi numbers. If we convert to our normal Roman numbers, it will be like this. It is 386. So it's 386. But this is not AD. This is our it's Nepal Sambat 386. So the findings in this article are based on the study of 65 inscriptions out of a total of 200 inscriptions reported to be found so far, not only in Changunaren, in many other places in Kathmandu Valley. The inscriptions were carved mainly on the stone slabs. One of the example I have put over here, some stone pillars and metallic objects that were found in and around Kathmandu Valley. The initial number system was Brahmi numerals. Brahmi numerals were used around 1st century AD in India and in south to mid Nepal. The Ashok pillar in Lumbini, the birthplace of Buddha, has this inscription. So this is the in Lumbini, the Ashok pillar. So you may be very surprised. I visited Lumbini in 2013 साल. You can just imagine. I visited Lumbini in 2013, 2013 साल, and there are almost nothing over there. So in this pillar, Ashok has made an inscription over there, where he said Buddha was born over here, and so on and so on. And 1/8 of this government tax were reduced, and so on and so on. But we are interested in numbers, so I'll show the two numbers over here. One number is here. This number, what is written, it is written in Brahmi numericals, it gives 20 number. There's one more, I think, but anyway. And the statue with Brahmi inscription over there at its base was found in May 1992 in Maligaon. So in Kathmandu Valley, this was one of the oldest inscription, which interest of our is number. It's in Maligaon, and is considered to be the first historical epigraphic record found in Kathmandu. So the number is here. And this is number 107, which that is Nepal Sambat, and it converts into 185 AD. This is 4. Actually, not Nepal Sambat, Lisabi Sambat, this is called. And there's another number also, 4. So this is our interest of numbers. So numbers had been used in Nepal, you can see, very in ancient times. So Lisabi numbers are a modified version of Brahmi numbers. The upper one is the Brahmi, the lower one is our Lisabi numerals. And you see, 1 to 9 is 1, 2, 3. It also is very, this 1 to 3 is very close to Chinese character also. Chinese also write 1 bar, 2 bar, 3 bar, and so on. But you can see 10 is written with a new symbol, and if you add 1 to 10, this is 1 to 10, it becomes 11. And so you can see to write bigger numbers, you go on adding over there. So until this time, there was no 0. So for every big numbers, you have to invent new numbers. So 10 was written like this, 20 as the symbol is like this, and 20 and 1, 21, so on. So 10, 20 uses separate symbols. The compound numbers like 11, 12 are represented by juxtaposition unit symbols with ligature. This is ligature. And if you make it juxtaposition with these symbols, then you will turn into 12, 13, and so on. So that is how our Lisabi numerals were used. 100 symbol is represented by this number, look like so. 200 by, so this is 100, and if you put 1 over here, it will turn into 200. And 300, 2 more lines over here, and 300, and so on, so on. 400, 500 are represented in this way. And the bigger numbers, like 400, 500, 600, are formed by attaching 4, 5, 6 to the symbol 100. So to the 100, if you add this, is 200, 300, 400, this is 4, this symbol for 4. So 400, 500, so because 0 was still not in use at the time. The numbers found on the inscription are mainly date in Sambat year, which lacks by 78 years. The bigger numbers are written as follows. The 386 I have already shown. So it's in the decimal system. 300 means 3 into 100 plus 1 into 80 into 6 into 1, 386. No clue found so far about the arithmetic of Lisabi number. We don't know how they use the arithmetic. Symbol of 0 and its use not found. Some earlier writings, not Lisabi, have used a symbol which looks like 0, just like 10 was written like this, with 0 something like 20, 30, 40, 50. So this type of symbols were also used in Nepal. Now, that's more than enough. That is what there are a lot of slides of that Asian Mathematics Conference. Now, to make you interesting, I'll start with a perfect number. I know all of you know this is perfect number. A perfect number is a whole number, an integer greater than 0. It's a whole number greater than 0. And when you add all of the factors less than that number, you'll get that number. For example, the factor of 6 are 1, 2, 3, and 6, of course. So we don't take the 6. But if you add this 1 and 2 and 3, you get the original number 6. So 6 is a perfect number. For example, 28 have the factors 1, 2, 4, 7, 14. And 28 we don't take as the sum. So 1, 2, 4, 7, and 14 is equal to 28. So 28 is also a perfect number. Then the question arises, how do you find the perfect number, and how many perfect numbers? What is the biggest perfect number so far found out? For example, 496 is also a perfect number, and 8,128 is also perfect number. You can just count over there later on. So one of the interesting number is number called perfect number. So once mathematicians, what they try to do, they like to generalize it or convert it into a general form. The first 5 perfect numbers are 6, 28, 496, 8,128, which I have shown. Also this 4096 into 8191 also is a perfect number. This is 5 perfect numbers. So if you look at carefully, then you can convert it into a mathematical formula. We can write this pattern as power of 2. You can see it is power of 2. You have 2, 2 to the power 2, 2 to the power 4, and so on. So it looks like power of 2 into double that power minus 1. So if you write mathematically, it will be perfect number is 2 to the power n minus 1 into 2 to the power n minus 1. You can see. So then we have, for a perfect number, we have a general formula. But we are still not sure whether this formula will always yield a perfect number or not. So with this small introduction, now I come to our topic from 0 to infinity. So I'll start with 0 and conclude with infinity. But before that, let me show two quotes about numbers. So Pythagoras at that time in Swiss told that number rules the universe. The whole universe is ruled by number. And more interesting is the next quote, quite recent one, I'll say. This Nikola Tesla. So Nikola Tesla is 1856 to 1943. He is now the modern name for his birthplace country is Croatia. He says that if you only knew the magnificence of 3, 6, and 9, then you would have a key to the universe. So the 6, 9, 3, 6, 9, and combination of these numbers will open us to the universe. That is what Nikola Tesla said. And coincidentally, within these 24 hours, something happened in my house. This happened in my house. I have this slide. You can see yesterday I got the number of my house. In the evening, yesterday, I found this house number fixed on our gate. Only yesterday, September 30, 2021. This photo was taken today morning by my wife on October 1, 2001. You can see I have 396. So I am living in a house which is something symbol of universe. So coincidentally, it happened like that. So I thought that I should show this house number 396. So I'm lucky. So mathematically, I'm lucky now. Now let's go to our topic. Of course, I have to start from 0. In our seminar 2S2, I have already talked about 0. If you look at 0, you see nothing, but looking through it, and you'll see the world. That is what the Vedic mathematics has told us. So it's from Vedic mathematics. So I don't talk too much about 0 today. Last time I have shown few slides related to 0 in S2. But I'll try to quickly recollect, which all of you know from school level, that the number systems are natural numbers, 1, 2, 3, and we have the whole numbers where we include 0, and we say 0, 1, 2, 3 are the whole numbers. Then we have the integers. We take the negative parts also, minus 3, 2, and so on, integers. And then the rational numbers, which is P by Q. P and Q are integers. You all know, so I'll quickly go through it. So all terminating finite decimals are rational numbers. All non-terminating, non-finite, but recurring decimals are also rational numbers.
So excuse me.
So
I'm new participant of this day. So I want to know that is 0 is even number or odd number? If you don't mind, please give me information about that.
So, excuse me.
Let me show you, give an example. So you have been to Germany? No. So in Germany, there is a Berlin. Okay. If you, at my time, when I was in Russia, it was East Berlin and West Berlin. So if you put your leg between these two boundaries, then tell me where I am in East Germany or I am in West Germany. West Berlin. What do you say? Huh? What do you say? I am in East Germany or West Germany when I put my leg within these two. Even there was a house where one opening of the gate was in East Berlin, another was in the West Berlin. Now, where this house stands, in East Berlin or West Berlin? So in the same way, 0 lies between negative part and positive part. So according to your convenience, you can move it this side or you can move it that side, because minus something tending to 0, plus big numbers also, if you decrease it, it will tend to 0. So then it is in the middle part. So middles are those which you can't say that it lies on the left or right. Even it's not a very good example. Mount Everest top ma garden, Chinese like this is my top bhancha, Nepali this is my top bhanera हामीले फुर्ती गर्नुपर्छ. So when you are in the boundary, don't make them separate. Put them equal to both sides. Okay, that's my answer. Anyway, So irrational numbers are there. So these numbers can be written as fractions with integer, numerator, and denominator. We all know that. Real numbers are there. Real numbers are these rational and irrational numbers together, and they form a set of real numbers. They are imaginary numbers. I am not talking about them. I am just trying to show that they are complex numbers. There are also different type of numbers about which some of them come in the later phase. I am just trying to recollect those number systems and the symbols used to represent these numbers. And there is one word which generally students, math education students knows it, but the pure math students, they don't know. When I ask what is numeral, they are confused. And you must be knowing that numerals are a representation of these symbols for the numbers. So I have shown numerals of Elizabeth period, Brahmi period, and also here we are writing the Latin one. Anyway. Now, just for your curiosity, I am putting here just a, you can say it a practice for you. In how many ways you can prove this theorem that the number root 2 is irrational? So, and I think there must be 5, 6 methods in which you can prove the theorem the number root 2 is irrational. Because geometrically it means it is a diagonal of a square, and diagonal square is not commensurable. That means you can't measure exactly which is sides. And commensurable segment means any segment which would be contained in both an integer numbers of times, and so you can't do that. So try to prove this theorem, which will be useful for if you have a teacher in school or even +2. Now, another number, which we have already told a little bit, generally transcendent numbers and algebraic numbers. Algebraic numbers are a complex number alpha is said to be algebraic if there is a non-zero polynomial px with integer coefficients of which alpha is a root. So complex number also includes real numbers. When the imaginary part is absent, it turns into real numbers. So rational number is the solution for the polynomial equation qx minus p. Because if you put px is equal to 0, then you will find the value of x is equal to p by q. And root 2 is the solution for the polynomial equation x squared minus 2. And 1 plus root 5 by 2 is the root for x squared minus x minus 1 equation. And so these numbers, what we are saying, p by q or root 2, 1 by root 5 by 2, these are all algebraic numbers. Transcendental numbers, a complex number alpha which is not algebraic is said to be transcendental. So if you don't have a polynomial, a root of the polynomial, that number will turn into transcendental number. So this theorem was proved by Fermat and Linderman. His name has come earlier also. For any non-zero algebraic number alpha, E alpha is transcendental. E is also transcendental. Pi is also transcendental. The number E and pi are transcendental, about which I talked in S3 also, seminar 3. But very interesting is the prime number. Prime number is one of the interesting which has been exploring so far for so many centuries. And it is a p greater than 1 is a prime if it cannot be written as a product of two smaller positive integers. And it is a n greater than 1, that is not a prime, is called a composite. Of course, you all school people know it. Prime number within 100 is so much. So there looks a bit haphazard. There is no pattern how the prime number grows. One of the method for finding prime number, very primitive method for finding prime was given by Eratosthenes. It's called a sieve of Eratosthenes, that is filtering. Well, here I have the example of n is equal to 1 is equal to 4, number from 1 is 64. So 1 is the prime number, then 2, all multiplication 2 are cancelled. You can see these red are the multiplicative of 2. So we cancel and take 3. So this one is prime, this one is prime. Take 4, it is not prime, it has been cancelled. So I can take 5 and cross all divisible by 5. So 10, 15, 20, and so on, this 20, 35, and taken out. And so the remaining one here, after all this cancellation, take 7, and you have a cancellation over here. So the remaining one here is, what is remaining here? 2, 3, 5. So when you say prime, prime is greater than 1. So you should not take 1 as a prime number. It's only. So 2, 3, 5, and 7 are prime numbers within this 64. So this is one method of finding the prime numbers. Wait, sorry. कहाँ पुगेछु र मैले कि अर्कै चिजमा पुगेछु त ओके वाट गइहाल्यो ओके एनमा पुगेछ टिचर anyway so this is one method. There is a fundamental theorem of number theory. Every positive integer can be written as the product of primes. Every positive integer can be written as the product of prime. When we say positive integers, 1 is already excluded because positive now integer starts from 2. So any positive integer can be written as the product of prime, and this factorization is unique up to the order of prime factors. That means some prime factors, some 3 and 3 can be repeated. We can prove this theorem by a version of induction, which is sometimes called minimal criminal argument. I don't know whether you have heard this word, minimal criminal argument. We assume that there exists an integer with 2 different factorization. In a letter to Leonard Euler in 1742, Christian Goldbach put forward this conjecture, where this minimal criminal comes into word. We assume that there exists an integer with 2 different factorization calls such an integer we'll call criminal. There may be many criminals, but we consider the smallest one of these 2. So the 2 different are, n can be written as P1, P2, P are primes, Q are so other type set of primes. So if we suppose that n can be written as product of these 2 different type of primes, then you'll call it contradictory, and it will say that only a unique representation of a positive integer is a product of prime numbers. There's another theorem called, so that's the fundamental theorem. Now, that is fundamental theorem of number theory. Here I have another theory known that there are infinitely many primes. So when we use this word infinity, proving such a theorem is very, very difficult. This theorem was proved eloquently by Euclid himself. There are some more conjectures related with primes. The conjectures are such a true-looking fact which has not been mathematically proved. This is known as twin prime conjecture. There are infinitely many twin primes. Twin primes are 3, 5, where is separated by only 1 unit, are called twin primes, 3, 5, 11, 13, 17, and 19, and so on. So 2 prime conjecture, there are infinitely many twin primes. Not only primes are infinite, but twin primes are also infinite. Every integer larger than 2 can be written as a sum of 2 primes, and this was conjectured by Goldbach himself. So, for example, 12 can be written as 5 plus 7. 80 can be written as 13 and 67. You try for in how many ways you can write, in how many ways you can write 100 as a sum of 2 primes. For every integer k, there exists k conjugative composite primes. Okay, k integers. For every positive k, there exists k executive. That means once you have a prime, then there will be positive conjugative integers, composite integers, then the next prime will come. Then how do we find this sequence? Let n is equal to k plus 1, then n factorial plus 2, n factorial plus 3, n factorial n are k conjugative composite numbers over here. For example, if k is equal to 3, n is equal to 4, we'll have 26, 27, 28 are 3 conjugative composite numbers. K is equal to 4, n is equal to 5, then we'll have 122, 123, 124, and there you can see they are composite numbers. So with regards to prime, there are a lot of conjectures and theorems. So one question is, how many primes are there up to a given number? Of course, it has been said that prime numbers are infinite, but how do we find how many primes are there up to a given number n? We have found that for 64, there are only 1, 2, 3, 4, and 5. and 400. I have shown the list over there. Now the question is, how many primes are there up to a given number? So let's denote the number of primes up to n by pi n. An exact formula for pi n is certainly impossible to obtain, but there had been some approximation formula, which is known as the prime number theorem. Let pi n denote the number of primes among 1 up to n, then pi n will be approximately equal to n by log n. Log n is, generally we write ln, whereas the log is based with e. This was proved by Hadamard and De La Valle Poisson proved it in 1996. More facts about primes. Chebyshev, a Russian mathematician, proved in the last century that there is always a prime number between n and 21, n twice 2n. If you take any value of n, and there will be a prime between n and twice n. It is now proved that there is always a prime between two consecutive cubes also. Now, with regards to prime, the most interesting work was done by Pierre de Fermat, we call Fermat, 1691-1695. He has two very interesting theorems. One is called Fermion'S little theorem. If P is a prime and A is an integer, then P will divide, this prime will divide a to the power P minus A. For example, if you take P is equal to 7 and A is equal to 6, then you will see that 6 to the power minus 6, which will give us 279930, which will be divisible by 7. You can check. Now, some questions. How do you decide whether or not a given number is prime? If you have big number, how do you decide whether it is a prime? If it is even, then you don't have to test. It is not prime. It is composite. But if it is odd big number ending with odd number, then it's very difficult to decide whether or not a given number is prime or not. So how to find a prime factor of a number is another question. For that, let's make a definition. We say that two integers are relatively prime if their greatest common divisor is 1. Now, with that, I leave over here and come to a ready-made presentation, which was given by Joy Frost and Joyce Frost, maybe two brothers, I don't know. One is from the University of Washington and another is from Lake Washington High School. So they may be in the same Washington vicinity. So I got 6-7 slides or 10 slides I'm using from their presentation, which is very interesting. So, of course, we already know prime numbers are the very atoms of arithmetic. The primes are the jewels studied through the vast expanse of infinite universe of numbers. So the primes are studied through the vast expanses of the infinite universe of numbers that mathematicians have studied down the centuries. So this was said by Marcus de Sauté in the book The Music of Primes, History and Exploration Prime Numbers, dedicated. So this is their slide. So this slide was dedicated to Royal Pennell, 1923-2008. He was a math teacher and prime enthusiast. So here in this slide, he talks about four categories of prime, named and notorious prime. So one is early primes, named primes, hunting for primes, and harnessing prime. I'll quickly go through these historical facts. So it starts with Euclid of Alexandria, 325-265 BC, the only man to summarize all the mathematical knowledge of his time. So in his book, in Proposition 20 of book 9 of these elements, Euclid proved that there are infinitely many primes. That has become the fundamental theorem of numbers. So this is what it was written here in this book 9, Proposition 20 of the Euclid book written by Euclid of Alexandria. And if you translate it, it says that a prime number is more numerous than any assigned multitude of prime numbers, which simply means that prime numbers are infinite. So I have talked about this Eratosthenes sheep. So Eratosthenes is of Cyrene is proper name, 276 to 994 BC. He was a librarian of the University of Alexandria. You can say even about 200 before BC, there was a library in Alexandria. There was University of Alexandria, and he was a librarian over here. He invented an instrument for duplicating the cube, measure the circumference of the earth, calculate the distance from the earth to the sun and the moon, and created an algorithm for finding all possible primes called Irrational shifts, which I have already shown. So this mathematician, let's say, of that before century, before Christ. And there are another Nicomacheus of Geracia, about 100 AD. Now we are coming to our AD. Introduction to Arithmetic, he has written in his chapter 11, 12, and 13. He divide odd numbers into three categories. So even odd numbers, he made a categories of three type of categories: prime and incomposite, and composite, and a number which is in itself secondary and composite, but relatively to another number is prime and incomposite. So he tried to categorize the numbers in this way. In chapter 13, he describes irrational shifts in excruciating details. So he has given all the details over here. So more people who work on prime numbers. So as told, Pierre de Fermion'S is the most important person regarding the prime numbers, 1601, 1665. So about Fermion'S listed theorem, I have told over here, if A is a whole number and P is a prime, that is not a factor of A, then P must be a factor of the number A to the power P minus 1 minus 1. Mentioned in a letter in 1640 with no proof, and it was later on proved by Euler in 1736. Later on, we have a separate talk about brilliant mathematician Euler. Well, something is here on Euler, 1787, 1783. Euler proved a stronger version of Fermion'S little theorem to help test for Euler's probable primes. If P is a prime and A is any whole number, then P divides only evenly into A to the power P minus A, about which I have already talked and shown an example. Then came Carl Friedrich Gauss, very strange type of mathematician, you can say at the age of 15, he received a table of logarithm and one of the primes for Christmas. He noticed that primes are distributed to approximately the same which we have written here. Pi of n will be approximately equal to n by log n, now called the prime number theory. So first mentioned it in a letter 50 years later, afterward. And then comes the Riemann, Bernhard Riemann, 1826, 1860. One of the $1 million problems is the Riemann hypothesis. All non-trivial zeros of the zeta function have real parts of 1/2. So zeta function is written like this. So that means it is sum of ns divided by ns minus 1. So it's a series over here known as zeta function. And if you try to find the zeros of the zero function, then it's called Riemann hypothesis, and we get some solution for the prime numbers. So that was all the primes. Now named primes, some different names for the primes, which we have most probably we have not heard about it. Absolute prime. So I think we have not heard this word known as absolute prime. Also called the permutable primes are absolute primes, such a prime that I will not read it. For example, 337 is permutable because 337 is a prime, 373 is also prime, 733 is also prime. Most likely in base 10, the only permutable primes are 13, 17, 37. That in 13 is prime, 31 is also prime, 17 is prime, 71 is also prime, 37 is prime, 73 is prime, and so on, so on. So about 337, we have 37 over here. We have already said about it. So this is called absolute prime. Then there is another word called Cullen primes. Dr. James Cullen, yes, has interested in the numbers n to the power 2n plus 1 denoted by Cn. He noticed that the first C1 is equal to 3 was prime, but with the possible exception of the 53rd, the next 99 were all composite. Later, Cunningham discovered that 5591 divides C to the power 53 and noted these numbers are composite for all n in the range 2 up to 2000 with the possible exception of 141. So there's another name called Cullen prime. Cullen primes of the second kind also are there. 5 decades later, Raphael Robinson showed C141 was prime. The only known Coulomb primes, Cn, are those with n is equal to 1, 141, 4007, and so on, so on, so on. So there are certain Coulomb primes. These numbers are now called the Coulomb numbers. Sometimes the name Coulomb numbers is extended to also include the Woodall numbers, Wn, n to the power twice n minus 1. These are then the Coulomb primes of the second order. So I have borrowed this slide to show you that there are so many different primes number which we have never heard. Of course, this one we have heard, Fermion'S prime. Fermion'S primes are numbers of the form 2 to the power n plus 1. Fermion believed every Fermion number is a prime. Fn is a prime for n is equal to 1, 2, 3, 4, up to s is prime. Fn is composite for n lying between 4 and 31. But no one knows if there are infinitely many Fermion primes. But after 31, there may be primes. We don't know. There's Euler PRP, also prime number. Euler was able to prove a stronger statement of Fermion's little theorem, which we then used as to test for Euler probable primes. We use Euler PRP, n is composite. Then we say that n is Euler pseudo primes. And there is Ferrius prime. Ferrius prime is the largest prime found before electronic calculus. Ferrius prime is 1 upon 27 into 2 to the power 148 plus 1. So this is the bigger number. It is only prime number because you can say it's a odd number and it has shown that it is a prime number. So many new primes are there, and so I told people are working very in different aspect of the prime numbers. There's also called Fibonacci number. About Fibonacci number we'll talk in the next presentation. So if Fibonacci prime is a Fibonacci number, that is prime. So Fibonacci number are 1, 2, 3, 4, 5, 8. And so these 2, 3, 5 are Fibonacci prime for 2, 3, 5, 18, 89, and so on. So within the Fibonacci numbers, there are certain primes. If you take out the primes only, it will turn into Fibonacci primes. Sophie-Germain prime. So Sophie-Germain prime. A Sophie-Germain prime is a prime P, so that Q into 2P plus 1 is also prime. So if you find a Q which is 2 plus 1, then we call it a Sophie-Germain prime. Around 1825, Sophie-Germain proved that the first case of Fermion's last theorem is true for such prime. That is, if P is a Sophie-Germain prime, then there do not exist integer x, y, and z different from 0, and more a multiple of P such that x to the power P plus y to the power is equal to z pi. Of course, we have will several times come across this Goldbach's conductor. Every even number is a sum of two primes. Has been verified for all even numbers to 400 trillion, but still not yet proved. And there is another prime known as Lucas prime. About Lucas prime, Lucas number will come later on also. A Lucas prime is a Lucas number that is prime. The Lucas number can be defined as follows: V1 is equal to 1, V2 is equal to 3, and Vn is equal to Vn plus 1 is equal to Vn plus Vn minus 2 for all n greater than 2. Lucas numbers are like Fibonacci numbers. Fibonacci numbers start from number 1 and 1, but Lucas number starts with 1 and 3. So 1 and 3 will give us 4, 4 and 3 will give us 7, and so on. They are called Lucas numbers. So within a Lucas number, you can also find prime numbers. And there is another interesting prime known as Mercenary Prime. So Mercenary primes are the primes of the form 2 to the power n minus 1. Mercenary claims that n is in 2, 3, 5, 7, 13, and so on. You can see would L primes. A Gaussian Mersenne prime is a prime using Gaussian integer. That is 1 minus 1, I minus I, and so on. There is another one called Landry and Aurifieri. The mathematician Landry devoted a good part of his life to factorizing 2 to the power n plus 1, and finally found the factorization of 2 to the power 58 plus 1 in 1869. So he was essentially the first to find a Gaussian Mersenne with n is equal to 29. Just 10 years later, Aurifieri found a Gaussian factorization which would make Landry's massive effort vital. He could find this factorization in a simple way. There's again Lucas Leyren number. A Lucas Leyren test is an efficient deterministic primality test for determining if a Mason number mn is prime. A Mason number 2 to the power n minus 1 is prime if it divides the Lucas-Mehler number called nn, where ln is equal to ln minus 1 to the power square minus 2, and so on. And there's also another word known as planidromic prime. A planidromic prime is a prime that is planidromic. Planidromic means where you can read from left to right, it becomes the same. A pyramid of planidromic prime was given by Honecker Jr. So 2, here you can see 30203, 13300. So you go on adding left and right, and in some way, so these are planidromic primes. Yes. And there's another word called royal prime. Royal primes are primes where the digits are all primes, and a prime can be constructed through addition or subtraction using all the digits. These are named after Royal Pennell. So it was given by this mathematician Royal Pennell. That's why it's called royal prime. He was a Royal Pennell. He was the treasurer of the Puget Sound Council of Teachers of Mathematicians, so in abbreviation known as PSCTM, from 1973 to 2005, and who was born in 23rd, the first royal prime of the century. Anyway, there's another word called rep unit primes. The rep units are positive integers in which all the digits are 1, denoted by as R1 is equal to 1 is prime. We don't take it R1 as prime. R2 11 is prime. Of course, you can see these big primes with one. This is also a prime number. This 111 is also prime number. So here we have with 2 digits, 19 digits. I have here 23 digits. So rep unit primes are 3117 is 10 to the power 317 minus 1 divided by n, and so on. This is R1031 is all prime. In 1919, Dubner discovered that R49081 was a probable prime. In 2000, Baxter discovered the next rep unit probable prime, R468453, and in 2003, it's still going, discovering, known as Dubner identified R109297 as a probable prime, and so on. And there are twin primes I have already told about. The 2 primes are primes whose difference is 2. Conjecture, but not proven so far, that there are infinite number of twin primes. All twin primes except 3, 5 are of the form 6n minus 1 and 6n plus 1. The largest known twin primes are this with positive plus 1 and this number with negative 1, with 11,713 digits. It was found by Indel Fair and Zere in 1995 only. And that's a twin. Now we also have a cousin prime. Cousin primes are primes whose difference is 4. That was difference was 2, the 4, 3, 7, 7, 11, 17, 23, 4, 3, 4, 7 are some example of these cousin primes. And there is also known as sexy prime, not related to sex, but related to 6. Sexy primes are primes whose difference is 6, 11, 17, 13, 19, 17, 23. So you can see there are so many types of primes, and of course we are talking of numbers, and primes are numbers. And there's Well-Ferris prime by Fermion'S little theorem. Any prime p divisible by 2p minus 1. A prime p is Well-Ferris prime if p square divides the whole numbers. Not only p square also divides the whole number. So 1903 and 3500 are the only known such prime. And they have been checked for at least so many. This is a strong statement. In 1910, Mirimanov proved the analogous theorem for 3, but there is little glory to be found, so not much too of interest. Such numbers are not Mirimanov primes. So that was named prime. Now hunting for prime. So one way of hunting for prime was Eritreus sheaves. Euclid proved there are infinitely many proofs, and this a into n is equal to a into b into c into p plus 1. N is greater than a, b, c, and p. If n prime, then it is larger than the others and not included in the list. If n is composite, then one of the a, b, c divides n and divides n minus a into b into c, which is 1, which is impossible. So there are infinitely many prime. That's one of the way of proving. Gauss and Legendre. Gauss noticed the frequency of primes approach n divided by log n, but didn't publish. Legendre noticed that frequency of prime approaches n upon log n minus 1, log n minus 1.80361,106, and published in 1808, finding that yet again Gauss had been first. Gauss had found it first, but he didn't publish, so Legendre published it. And if you are interested, you can go to how many primes, and then from there you can find all these different type of answers. So summarizing this, we have the prime number theorem. Gauss mentioned in a letter, but did not prove, as it has been said, that number of primes less than x can be approximated by the integral du by log u, from 2 to up to x. Proved independently by Jacques Hadamard of France and Charles de la Vos of Belgium in 1996. Peter Gustav Legendre Dirichlet used Euler's composition of primes to the zeta function to prove Fermion's conjunction about infinitely many primes, modulo 1 to n base. So when we have to prove this Fermion's theorem, we have to use this modulo mathematics. So zeta function, it has been said that its value can be calculated by 1 to the power x, 2 to the power x, 1 upon 3 to the power x, and so on. We have to find the zero of this equation. Then Gauss introduced pi x pi, so for a certain number of primes less than or equal to x. Riemann showed that the zeta function can also be written as a product of over its zeros in the complex like this one. So this will give us zeros. So if you put the value here, it will turn into 0. So for the techniques of adding waveforms to model complex graphs, Cauchy word of complex numbers and Dirichlet's fascination with Euler's zeta function are basic to Riemann's conjecture. The real part of any non-trivial zero of Riemann's zeta function is it will be in the line x equal to half. So the different shapes for prime numbers are, we have talked about Erotosis shapes are there, axial shapes are there, quadratic shapes are there, number filters are there. So quadratic fields is given here. I'm not going to read over here because this is not my slide. And there's number field shapes over there. And great internal prime source is still going on. There are a lot of opportunities. On September 4, 2006, Dr. Curtis Cooper and Dr. Stevens Ullens, there's computer team, CMSU team, discovered the 44th non-Mercenary Prime in 2006. And it was more Eden Smith using GIMPS, digital computer programming, found 2 to the power 43 minus 1, about 12.9 million digits. It was in August 2008. That was in 2006. This is in 2008. Winning the 1 million prize from Electronic Freedom Foundation. Prime generators, they are also function to generate primes. The most frequently used is fx equal x square plus x plus 41, else prime for x less than 41. Because if you want to use computer, we have to have a certain formula and then logarithm to generate that formula. So in no polynomial known with greatest all and only primes, but this generates only primes and negative primes. So it's a big formula over here which generates primes over here. And lastly, harnessing primes. So harnessing prime is still going on. Every number can be expressed as a unique product of primes, which I have already showed. For example, 450 can be written as 2 into 3 into 5 into 5. The greatest common factor is the product of the list of shared factors. So we know how to find greatest common factor, CGF. So we factorize it, and then you find over here. This finding GCF is very important. Now we are in the computer age, and here most of the computers are used on this GCF and also LCM. The least common multiplication can be found by writing the prime factor. So everywhere you have to make prime factorization. When you go into cartography, then you need 2 bigger primes, and to find bigger primes is a problem. And for all this testing of microprocessors and all these are based on these prime numbers. So all this communication also based in prime number. That's why a lot of works, even quantum theory, they have to use prime numbers. So that's why prime numbers is the word itself is prime, is a very prime number. So I'm not going to reading over here. So there are bet over here. Non मैले फेरि अर्कै ठाउँमा थिचेर मेरो जहिले पनि त्यहाँ अर्कै ठाउँमा थिचेर हेर्नु पर्दो रहेछ. ओके कहाँ पुग्यो. धेरै तल पुगिसकेछु अब. Winning base. Doug Jagger, who argued against Siemens' hypothesis, bet 2 bottles of wine that an exception would be found in the first so many roots. Yet Dodge's team calculated an extra 1,000 million roots to help with the bet. These were the most expensive bottle of wines because it's a bottle of wine, but the cost is very expensive. Wait, फेरि मैले त्यसैमा थिचेर हैरान भयो. Okay. So all our encryption is done with RSL. RS is from the abbreviation of Ron Ribes, Eddie Samir, and Len Edelman. So they harness Fermion'S little theorem, and all our encryption is what we have in computer and in mobile system. All these are based on RSS encryption. So that was named and noticed primes I have found from this gentleman over there. Anyway, now coming back to my presentation. So as I showed, the most work on an interesting work, an important work was done by Fireman. He's from France, related with prime numbers and other numbers also. Effectively invented modern number theory. So our modern number theory was invented by Fireman. He discovered several new patterns in numbers which has defeated mathematicians for centuries. Fireman identified a subset of numbers, now known as Fermion'S numbers, about which we have already talked, which are of the form of 1 less than 2 to the power of 2 to the power twice n plus 1. He discovered that every single prime number that divisible by 4 and leaves a remainder of 1 can be expressed as a sum of 2 squares number, now known as 2 square theorems. For example, 5 I can write as 1 square plus 2 square. 13 I can write as 2 square plus 30. 241 I can write as 2 plus 51. So these are not a 2 square theorem. And we have the most important known as Fermion'S last theorem. Fermion started looking at work done by Greek mathematician Diophantus, 2284 AD. Diophantus, often known as the father of algebra. You can see this, there's a controversy on Diophantus. Some say that he is from 2000 to 200 to 184. In some books, it is written as 200 to 280 AD. Often known as the father of algebra, is best known for his arithmetic. The book is arithmetic, but it also relates with algebra. A work of the solution of algebraic equation on the theory of numbers. The book itself is known as arithmetic, but it is related with solution of algebraic equation. Arithmetic is a collection of 130 problems giving solution to determinate equations and indeterminate equations. So this is the first cover of Alexandria, Diophantus by Alexandria. It's called Arithmetica. Though it has been said that it's more related with algebra, but the book is called Arithmetica. These are some pages from that book over here, because this page is important. So in the margin of his copy, that is Fermion'S copy, his copy of Diophantus, Arithmetica, problem number 8, Fermion wrote, to divide a cube into 2 other cubes, a 4th power, or in general any power, whether into 2 powers of the same denominations above the second is impossible, and I have assuredly found an admirable proof of this, but the margin is too narrow to contain it. That's what Fermion'S wrote on problem number 8 in this book, Arithmetica of Diophantus. And this, the theorem originally described in a scribbled, not very readable, note in the margin of his copy of Diophantus Arithmetica says that no three positive integers a, b, c can satisfy the equation a to the power b plus b to the power n is equal to cn for any integer value of n greater than 2. This seemingly simple conjecture has proved to be one of the world's hardest mathematical problems to be proved. So this is his last theorem, known as Fireman's last theorem, FLT. If n is greater than 2, then the sum of the n power of two positive integers is never the nth power of positive integer. So that means a to the power b, a to the power n plus b to the power n is not equal to c to the power n. A, B, C are real numbers. R anyway. Fermion'S claimed in a note that he proved this, in a note actually, but he never wrote down the proof. Only in 1995, Andrew Wills, British mathematician, in one part with the help of Robert Taylor, finally proved it. Because when Andrew Wills claimed that it has been proved, there was a small hitch mistake, and Robert Taylor added and made a correction and got the final proof over here. Wells first announced his proof on 23rd June 1993 as a lecture in Cambridge entitled Modular Forms, Elliptical Curves, and Galois Representation. However, in September 1993, the proof was found to contain an error. 1 year later, on 19 September 1994, in what he would call the most important moments of his working life, Wells stumbled upon a revelation that allowed him to correct the proof to the satisfaction of the mathematical community. The corrected proof was published in 1995. Together, these two, the two papers which contains the proof are 121 pages long. You can see a proof of this seemingly very simple statement has 129 pages. The lore surrounding Will's proof is the 7 years he worked on the problem in secret. So you can see what is the dedication of Fermion'S in to prove this, Will's dedication to prove the Fermion'S last theorem. Okay, now there's more than enough for prime numbers. Now we go to leftist number. So this was the presentation I made in 2010 in Viratnagar, the National Conference of Mathematics. When I became the president of Nepal Mathematics Society, then we decided that we'll have a biannual national mathematical conference in different parts of the country outside Kathmandu. So the first one was in Viratnagar. And so then I also made a presentation called the leftist number. I don't know how many of you have heard about this leftist number. I don't know, but I'll give some slides to introduce you what is the leftist number. So this presentation was prompted by the article Leftist Number by Andrew Rich, published in the November 2008 issue of the College Mathematician Journal. It is published by Mathematical Association of America, MAV. Let's look at this geometrical series. Everybody knows this geometrical series. And if you put A is equal to 3 and R is equal to 10, then we obtain 3 plus 30 plus 300 plus and so on. And A is equal to 3 and R is equal to 10, then it will give a 3 upon 1 minus 10, which is equal to minus 1 over 3, which looks totally absurd because sum of all positive bigger numbers is giving us the value minus 1 by 3. So the sum of positive node is negative. What went wrong? There must be some wrong because when we study this upper formula, then we say that R is less than 1. They say that. But as a mathematician, then we try to ask what happens if you put R is greater than 1. For example, I have put R is equal to 10 over here. Then we have this absurd type of result. So that's why we have to introduce this number called leftist number to make sense to such a summation. Real numbers represented as decimal numbers are typical seen as being fixed to the left with infinite tails on the right. For example, 1 by 7 is 0.1428 and so on, with repeating cycle. So in this case, I have a repeating cycle, 1428, because it's a rational number. So once it's a rational number, then we'll have a repeating cycle over here, recurring over here. Suppose the cycle is reversed to give over here. Suppose the cycle is reversed to give 0.7. You can see here it is 142857. So it is written 75I24171. So what will be the value for this one? It is 1 by 7 is giving this one. What will be this value? Or just 0.75I241 enough, because all the repetition. What fraction is this? It is 69 by 91. 61 by 91. But 1 by 7 can be written as 13 by 91. Now, if denominator is same, but here the numerator is 69, here the numerator 19. In contrast to normal real numbers, leftist numbers are fixed to the right with their infinite tails running left. A leftist number is a number whose digits terminate to the right and may continue infinitely to the left. Additionally, the negative sign is not used to denote additive inverse. So a bit different type of numbers. This creates a markedly different representation of numbers, and therefore the notice is slightly different. When there is a repeated series of digits, the standard notation from repeating decimal representation of fraction will be used. So it is something like that. When there is a repeating series of digits, the standard notation from repeating decimal representation of fraction will be used as 9 bar 7. That means there will be 9 and 9 so on. Representing the fraction will be used like this one. Signifies a repeating 9 to the left. So it is 9, 9, 9, 9, and 7. Terminating with a 7. Just to the left of the decimal. Likewise, if you write 091 and bar over 09, it represents a repeating series like this, 09, 09, 09, and the last digit will be 1. Unless written elsewhere in the number, the decimal point is understood to be immediately to the right of the rightmost number. So decimal point will be somewhere here. Here, decimal and 1 and so on. Although the leftist number itself may not be real, all digits of the leftist numbers must be real. How do you make addition and multiplication for such a leftist? The concept of addition and multiplication perhaps work more intuitively in leftist spaces as compared to the real space. Right, so left addition and multiplication between two real numbers always begins to the right of the number. For leftist numbers, they are based strictly upon the digits of the leftist numbers, which are real, and all leftist numbers have it rightmost digits. To add two leftist numbers, simply add each column together as though adding two reals, carrying the extra digits from each calculation to the next column to the left, repeating for infinitum. For example, if I add like this one, then it will be something like this one. Yeah, 7, 4 goes any. 1 hour, go on, it is good 0, 0, 0, and so on, so on. So now since here I have 6 repetitions over here, 3 will be repeating over here, and so addition will give such a number, whatever it is. Multiplication, for example, also will be done in the leftist way. Very simple one, 7 to 14, and 6 to 13, 6 to 13, and 6 to 13, and so it will go on repeating like this one. Decimal numbers are fixed to the right, and there is an implicit repeating 0 to the left. Therefore, the natural exists in leftist space in the same representation as real space. Again, 0 exists in leftist space with an understood interpretation of the repeating 0, and which have repeating in the leftist system, we put a bar. So it will look like that. It's still an additive identity for natural numbers, and one is the multiplicative identity. And this is the connection between integer and leftist number. By definition of leftist, a negative sign cannot be arbitrarily tracked onto a natural number to create the integers. Every natural must have an additive inverse such that when summed, they result in 0. Since a negative sign is inconsequential in leftist number, we don't have negative sign. We denote the additive inverse of x by x slash, so that x plus x slash x is equal to 0. All leftist numbers x has also additive identity such that x plus x slash will be 0 and so on. So when I read this, then I try to find about leftist number in the Google. Then I couldn't find anything. Then I wrote to the author itself. Then the author answered me, and you can see on 10/7/2009, he wrote me, I am sorry to say that as far as I know, the author itself wrote that, sorry to say that as far as I know, my article is the only one representing the topic in this way. However, as I said in the article, leftist numbers are closely related to pediatric numbers, and there's much written about them. Fernando Guevia, the Italian, has a Springer book on pediatric numbers, which goes into greater depth. I think you can find much there that will interest you. Thank you for interest in the subject. How are conditions in Nepal? I have always dreamed about visiting Nepal. Some years ago, we had a number of students from Nepal, but at the moment we have known Professor Rich in Manchester College. So this is our email corresponding regarding so not much has been done on negative numbers. So if some of you are interested, you can go and explore about this leftist number. Now, since he has said that it has very close connection with pediatric number, and we are talking of numbers, let's quickly look at what is pediatric number. I hope some of you must be knowing over here. So the rational numbers, the set of rational numbers is there, we know. So now we know this natural number, some of the rational numbers I have written. The set of rational numbers has a lot of holes. You can see there are lots of holes in it. There are different ways of filling these holes. Some of the holes are filled by transitional numbers also. One usual means of filling these holes creates the set of real numbers. To make sense of this, we need a notation called closeness. Two numbers are close if their decimal agree for a long way to right. We play a similar game to construct the pediatric number, except that we choose a new notation of closeness. Now we say that two numbers are close if their digits are the same for a long way to the left, not right. So once he has used the word left, then it seems that pediatric number is close to what is known as negative numbers. So the 10 pediatric numbers is given here, 0.003, 0.53, 630, and so on, are getting closer and closer together. That is the new concept of closeness. About pediatric number, P is some specific number, usually a prime, generally. Real numbers have definitely many digits. You want to say, or the pediatric numbers can always return with finally many digits, right? For example, is not a 10 pediatric numbers, but 3333.33, more 3 on the left side. On the left side is a 10 pediatric number. Sequence given in the previous slide converges to some new 10 pediatric numbers over there. So since it's a pediatric number is also very popular discussions on number theory, a lot of over there. So I read the pediatric number for you. Now simply go back once to Goldbach conjecture, since it has not been finally really proved. Christian Goldbach, March 18, 1690, November 20, 1764, stated that every even number that can be written as a sum of two primes. The same prime may be used twice, of course. One of the oldest unsolved problems in number theory and in all of mathematics, the conjecture is divided into two parts known as the weak and strong conjecture, respectively. The conjecture has had additions since Goldbach's original theory was presented. So Goldbach described his conjecture in a letter to Leonard Euler in 1742. Every number greater than 5, every number greater than 5 can be written as a sum of 3 primes, not 2 primes, 3 primes. So it is called a weak conjecture. Every even number greater than 2 can be written as a sum of 2 primes. This is more stronger. The weak one is sum of 3 primes. The stronger one is weak of sum of 2 primes. For example, 4 can be written as 2, 2, 6, and so on. But sometimes you can write in different ways. 10 you can write as sum of 2 prime 3, 7, or 5, 5, because you can repeat the primes also. 54 you can write as 7 plus 47, or 11 plus 43, and also 13, 4, 41, and 74, 37, and 24, 23 plus 31. So 54 has a lot of options for writing as a sum of 2 primes. There's also an extreme example. So this number is even number. You can see it's a number is a 5569 plus, and this is a big prime number. It's a sum of this small prime and big prime. Since 1742, others have tried to prove Goldbach conjecture. Eller noted that 1 is not considered to be prime, and this stated the conjecture back to Goldbach as all positive integers can be expressed as a sum of 2 prime. This alters the conjecture to read every even number greater than 2 or equal to 4 is the sum of 2 primes. So there are some primes. All conjectures has been researched, and majority of mathematicians believe the strong conjecture to be true. This is based on the statistical theory that the bigger the even number, the more likely it becomes that it can be written as a sum of 2 primes. In 1938, Esterman proved that almost all even numbers are the sum of 2 primes. Almost all even. All even when almost all. Also in 1938, Nipping verified the conjecture for all even numbers less than or equal to 10,000. In 1966, changing round proved that every sufficient large number, even number, can be written as a sum of 2 primes, or a prime and a semi-prime. Semi-prime is a number that is a product of 2 primes. And so in 1977, Pogorzelski circulated a proof, but his work was not accepted. In March 2000, T. Oliver Silva started distributing his computer source that has verified the conjecture up to 2 into 10 to be the 17 power to the 7, 2 into 10 to the power 17. His work is still going on. And finally, even the work of mathematicians can use the dollar to drum up interest. In an effort to sell a book on Goldbach's conjecture, a British publisher offered a million prize for a proof of a conjecture. That offer expired in 2000 and was unclaimed. So now you can claim it, of course. And now then, one new word, surreal numbers. I hope that nobody of you have heard this. I don't say. I think that you have not heard it. This is surreal number, very new one. Mathematician John Horton Cone first invented surreal number. Donald Knuth introduced them to the public in 1974. This Donald Knuth is the person who invented this text writing system. Surreal numbers can be used to analyze games. And so I am just introducing that. It's a very new number, surreal numbers. So recently I got one, this American Mathematics AM has sent me this journal from where I saw the surreal numbers. So I have not been able to make a presentation of the surreal numbers. So just one slide to introduce is this new type of number called surreal number, which is focused for research in the coming years. Now coming back. Now, since I started with 0, now I have to go to infinity. But before that, we conclude with 9, because in the number system, 9 is where everything almost ends. We are very close to 7 o'clock, but I didn't start at 5:30. So I'll take a few more minutes to talk about this 9, and we conclude. So this is 9 is very interesting. There are a lot of striking properties of numbers in general, and it's called a rule of nines. In July 9, 1997, there was an article in the Washington Post of July 9, 1997. The title was Beauty in Numbers from Place Value. It was written by D.R. Joy. Sundaram looks like some Indian origin. So D.R. Sundaram owns and operates an engineering research him in Columbia, Maryland. He is a engineer by profession, but he has interest in mathematics. You can see from this article, he has written Beauty in Numbers. He has published widely in both scientific journals and popular magazines. So this was on July 9, 1997. But I am not quoting any from this article. I have the copy of that article, but I will be quoting from his article next year. On May 13, 1998, he posted another article, the many mysteries of the number 9. So I'll quote some of his writing from this article, which was published on May 13, 1998. Quickly, I'll show this. The many mysteries of the number 9. I have taken the quote from his article. Although our modern numerical system is universally accepted as a language of mathematics and science, it was virtually unknown outside India, where it originated, until about the 8th century. So the first paragraph shows that this person is from India, is focusing on India. Until then, Europeans made do with clumsier type of system, including Roman numerals, and just try doing arithmetic with Roman numerals. And with doing arithmetic with mathematics with Roman numerals is nonsense. The Indian system of counting has been the most successful intellectual invention ever made on our planet. It was written by John Barrow, an English mathematician, writes in his recent book, Pi in the Sky. This is the title of the book. What makes this numerical system so convenient is that it is decimal cyclic. The fact that 9 is the largest possible digit in any given place gives rise to certain striking properties of numbers in general, termed the rules of 9. Several of these important rules are illustrated on the following slides. I'll give 9 rules, but I'll just focus on first 2, and the remaining 7 rules are some modification of rule 1 and rule 2, so which I'll leave you to study for yourself. Rule 1. When any number is multiplied by 9, if the individual digits in the resulting products are added, they'll always total 9, as long as you keep summing the digits produced at each step until you get one digit number. So this is rule 1. Let's see what does it mean. Rule 1. So if I multiply 1 by 9, I get 9. 9, 9, of course. Because sum of 9 is 0 plus 9, of course, 9. So, and 2 into 9 will give us 18. 1 plus 8 is equal to 9. 3 into 9 is equal to 27, which you can add 2 plus 7 is equal to 9. And so on. You can see even up to 10. 10 plus 9 is equal to 90. 9 plus 0 is equal to 9. So this is from rule 1. I'll also give some big examples. But here for this chart is very interesting. Here we have, you see, numbers 1, 2, 3, 4 in this sequence. Here I have, again, same number represented 1, 2, 3, 4. And here I have same number 1, 2, 3, 4 in the reverse way. So this is miracle of number 1. So for example, take any number, bigger number, 75893 multiplied by 9 will give us 683037. Add all the digits, you have 683037, add up 7, and again add 2 and 7, you'll get 9. So ultimately, from this rule 1, finally, when you come to one digit, it will be number 9. The rule 2, the converse of rule 1 is also true. That is, if the digits of a number.
Oh, one piece.
If the converse rule 1 also is true, that is, if the digits of a number total 9 or a multiple of 9, then the number itself must be a multiple of 9. For example, what do we mean by this rule 2? Example, consider number 1, 2, 3, 4. The sum of these numbers is 9. So 1, 2, 3 is divisible by 9, 9. You can see. For example, I can take 17982. Sum of this number is 27, which is multiple of 9. So this 17982 is divisible by 9. So this is rule 2. The other rules are, this rule 2 leads to another one, which I am not going to, you can read for yourself, but example is here and so on. So there are rule 5, and you can see it's very easy that if this is divisible by 9, this also will be divisible by 9. So combinations of these words are all divisible by 9. There are rule 5, which is also other combination of rule 2, and there are rule 5. You can see these 4 numbers in what order you change it, they are all multiple of 9. And there are rule 6. There are here. So I am not going to read it. The rules. There are 9 rules. So you can go. So very nice. But before I conclude, I'll show 3 slides which look interesting for me. So you can see that 9. Here I have 9. 1 into 9, 1, 2 into 9, 1, 2, 3 into 9. And if you add 2, 3, 4, 5, 7, you'll all the answer will be 11. This table was taken from the book Number Stories of Long Ago. One more slide. So that was multiplication of 8. It was 9. It was multiple of 9. And add 1, 2, 3, 4. You again get this type of number. You can see sequence number. So these 2 slides I have taken from the these 2 tables I have taken from the Number Stories of Long Ago. The book is like this one. So Number Stories of Long Ago by David Eugene Smith, British, published in 1919 over here. Now, almost last slide. So let's see the following slides of 0 to 9 over here. Okay, so this is numbers. These numbers, the numbers we write are made of algorithm 1, 2, 3, 4 up to 9 we know, called all Arabic algorithm, or distinguish them from the Roman algorithm. Romans have I, and so on. The Arab popularized this algorithm, but their origins goes to the phenomenological merchants that use the counting of their commercial counting. Have you ever asked the question, why 1 is 1, 2 is 2, 3, 3, and so on? What is the logic?
Sir, hello? सरको यो ब्ल्याङ्क आइरहेछ सर. आई थिङ्क
के आइरहेछ?
यो एकदम ब्ल्याङ्क आइरहेछ क्या सर?
ब्ल्याङ्क आइरहेछ?
यस सर.
हो?
सो त्यस्तै हो जस्तो लाग्छ मलाई. अरु सर म्यामहरुले देख्नु भएको छ?
स्लाइड देखिएको छैन.
ए म त्यसो अर्को किसिमबाट गर्छु है त एकछिन.
स्योर सर.
म त्यो ओरिजिनलले खोलिदिन्छु भन्ने न. ओरिजिनल खोलेपछि त्यो आउँछ. त्यो ओरिजिनल खोलेर ट्राई गर्छु नि. त्यहाँबाट
सरले नो सर, सरले त्यो शेयर गर्दाखेरि चाहिँ इन्टायर स्क्रिन गर्नुभयो भने बल्ल देखिन्छ कि जस्तो लाग्छ मलाई.
के हेर्ने रे?
त्यहाँ शेयर गर्दाखेरि चाहिँ सरले इन्टायर स्क्रिनमा सिलेक्ट गर्नुस् न सर.
ए अर्को किसिमबाट गर्नु पर्यो नि फेरि एकचोटि. पहिले त्यसलाई ओपन गर्नुपर्छ. पहिले यसलाई ओपन गर्छु अनि सेयर गर्छु. त्यहाँ आएको छैन है त्यो.
छैन सर.
किन आएको होला त्यो?
सरले कि एउटा विन्डो मात्र शेयर गर्नु भएको रहेछ, त्यही भएर त्यो मात्र देखियो. अर्को नेक्स्ट विन्डो गर्दाखेरि चाहिँ फेरि देखिँदैन.
ओके, पहिलाको मैले बन्द गर्नुपर्ने हुन्छ त हैन. म यहाँबाट गर्छु. आइरहेको छैन. अब देख्यो मेरो फाइल देखिरहेछ.
अहिले देखियो सर. हजुर यस.
फाइल देख्यो पनि यहाँ क्लिक गर्यो भने अब आउँछ होला. आयो
छैन सर.
किन आएको त? कोही
सर त्यो विन्डो भन्दा पनि
के गरेर आउँछ त?
सरले त्यो विन्डो भन्दा पनि यो इन्टायर स्क्रिनमा सिलेक्ट गरेर जानुस् न सर. त्यो भयो भने बेटर होला.
त्यो भनेको
पहिला चाहिँ सरले अनसेयर गर्नुहोस् हैन सर, मिटमा गएर. अनि फेरि त्यो शेयर गर्ने बटनमा क्लिक गर्दाखेरि त्यहाँनिर यो इन्टायर स्क्रिन भन्ने आउँछ नि सर. फर्स्ट अप्सन चाहिँ
स्टप प्रेजेन्टिङ गरौँ पहिला होइन?
हजुर है. फेरि प्रेजेन्ट नाउमा जानु सर. अनि यो इन्टायर स्क्रिन सेयर गर्नुभयो भने आउँछ.
Your entire skin. Okay.
अब चाहिँ सरले फाइल ओपन गर्नुभयो हुन्छ सर।
फाइल ओपन कहाँ गएर गर्नु क्या?
सरको फाइल अघि ओपन भएर बसेको छैन सर, त्यो पिपिटी वाला। यसमा होइन सर, त्यसमा क्लिक नगर्नुहोस्, त्यो पिपिटीमा जानुहोस् त सर।
यतामा
होइन नि सर, तल त्यो टास्क बारमा हेर्नुहोस् त, त्यहाँ सरले ओपन गरिराख्नु भएको जस्तो लाग्छ मलाई अघि। यसलाई उ गरे हुन्छ सर, यसलाई मिनिमाइज गर्नुहोस् न सर। यसलाई मिनिमाइज गरौँ, अनि सरको फाइल चाहिँ प्रेजेन्टेसन गर्ने फाइल चाहिँ ओपन गर्नुहोस् न सर। हो यही हो सर, ठिक छ। आयो सर, आयो। यस
आयो
हो सर।
ओके, थ्याङ्क यू। ल यहाँ हेरिसकेको छु है। यो क्वेसनबाट सुरु गर्छौँ। Have you ever asked the question why 1 is 1, 2 is 2, and 3 is 3? What is logic that exists in the Arabic algorithm? Very easy. It's very easy. They are angles. Check out this algorithm written in the primitive form. So 1, this is 1. It has 1 angle. We write 2, we have 2 angles. We write 3, there are 3 angles. We write 4, there are 4 angles. We write 5, there are 5 angles. You can see 1, 2, 3, 4, 5 angles. When we write 6, you will see 6 angles over there. When we write 7, there are 7 angles. But when you write 7, generally in European, they write that bar. In 8, there are 8 angles. Okay, there are 8 angles you can see. And in 9, you have to write in this way. Then you'll have 9 angles over here. So 9 angles. So that's why this 1 to 9 are related with these angles in the mathematical symbols over here. And the most interesting and intelligent of all is, of course, 0. 0. So there is no angle. It's 0 angle. So moral of the story, it is never too late to learn, and share this with your friends. Okay. Yeah. No? Stop presenting. Okay. मेरो स्लाइड अलिकति यो दुईवटा अझ प्रेजेन्ट गर्नु कहाँ छ यो?
सरले अघिकोमै त्यो स्टप सेयरिङ नगरिकन त्यसमै गर्नुभएको भए हुन्थ्यो। सरले अघि नै स्टप सेयरिङ नगरिकन त्यसमै गर्नुभएको हुन्थ्यो।
के हुने म निकालिहाल्छु त्यो।
फेरि सेयरिङ गर्नुहोस् न सर।
फेरि सेयरिङ गर्नलाई पहिला त्यो स्लाइडै चाहियो नि मलाई, होइन? क्विकली म त्यो स्लाइड निकालिहाल्छु। कहाँ जान्छ कहाँ छ? फर्केर आयो?
यस सर, यस आयो।
ल यहाँबाट सकिसक्यो यहाँबाट। ओके, there is another book by Ian Stewart called Taming the Infinite, because I have to end with the infinite. It was published in 2008. So this is infinite. The infinite symbol created by John Wallis, an English mathematician who lived and worked in the 17th century. Concept of limitness or eternity is there. I'll discuss more in seminar on sets. When I come to seminar on sets, which will be after the Saint-Hilaire. So I'll talk more about this infinity, because it's already 7:10. So next seminar will be in October 8, 2020. Because though the sign has started from October 7, but it is a Friday. It's a Friday, and we can still work on the Friday, I hope so. Then after that, we'll share the greetings of Dasai, and we'll meet after Tihar only. So next will be on Fibonacci numbers and golden ratio. Very interesting topic over there. Of course, since I started with numbers, now these are all related to numbers. So that's why I like to continue on October 8. There are more slides over there, which I'll leave it for you for self-study. So I will just quickly show here. There will be some repetition where so many new numbers will come over here. And so that will be enough for today. And we had a little bit over time in the sense that since we couldn't start in time, but I have done my job in 1.5 hours, full I hope so. So we'll meet next time. So after some time, because when this has 167 slides or something like that, I couldn't convert it into PDF, but I have converted it in another format, which you will get in a way. And also I'll separately send this angle slides, which is in a separate presentation. I'll send that slide also so that you can share and work with it. Okay, thank you very much.
Thank you so much, Bhadra Man sir. So it was really an interesting and very informative session, because so we have got opportunity to learn different kinds of number like perfect numbers, prime numbers, and there are various conjecture and theorems on prime numbers. Similarly, Fermat's last theorems and leftist number and other numbers. So I think the session, the topic of this session is also very much interesting, since we are discussing different kinds of numbers, so interesting numbers. So I think our participants have some queries or questions. The floor is open to you. If you have any questions, you can ask Bhadra Man sir. If you have
most of the materials has been taken by this book. म त्यहाँ राखिदिएको छैन यो 1 to infinity भने किताब छ मसँग यो 1 to infinity भन्ने किताब छ कि उहाँ त्यहाँबाट लिएको छ।
So if you have any question, you can ask.
छ के छ?
It's already 7 seconds.
के भन्नु खोजेको कसैले?
होइन सर, त्यो अर्कैबाट केही साउन्ड आयो।
र क्वेसनहरु चाहिँ यहाँ मेसेजमा राखिदिएको भए पनि मैले थाहा हुन्छ तुरुन्त। छैन मेसेजमा पनि, जसले बिचमै चाहिँ नि मेसेजमा राखिराख्यो भने पछि चाहिँ क्वेसन सोध्नु पर्दैन। मैले खुर्को त्यो मेसेजेस हेरेर चाहिँ नि इनकल मेसेज हेरेर चाहिँ नि एन्सर पनि गर्न सकिन्छ। किन यो अहिले नम्बर थ्योरी पनि सबैले नम्बर थ्योरी छ, बट स्टिल वर्क इज गोइङ सो मच द्याट अहिले यति नयाँ नयाँ नाउँको नम्बर आएको छ कि अब भन्न साध्य छैन। बिकज म्याथमेटिक्सहरू काम गरिरहेको हुन्छ के छ नेभर एन्डिङ नम्बर थ्योरी भनेको त
हो। भदन सर, एम आई अडिबल? यो हामी यहाँ त्यो केयुमा छौँ सर, यो ठ्याक्कै लाइट गएर
ठिक छ
स्ट्यान्डर्ड गयो क्या।
ल नो प्रब्लम।
ओके, सो सरको सबै सेसन्सहरू चाहिँ सो हाम्रो युट्युब च्यानलमा अभाइलेबल छ। यु क्यान गो वाच द भिडियोज तपाईँहरूको फ्री टाइममा। अनि अरू सरले जुन मेटेरियल्सहरू पठाउनु भएको छ, म तपाईँहरूको इमेलमा पनि त्यो फरवर्ड गरौँ न।
हुन्छ, भइहाल्छ।
सो थ्याङ्क यू सो मच Bhadra Man sir and all the participants.
हुन्छ, ओके, थ्याङ्क यू। ओके, गुड नाइट।
गुड नाइट
भन्ने टाइम आइसक्यो र साढे 7 भन्नु।
Thank you, sir.
Thank you.